start discussion on the design of computer instruction set and the CPU. First we will see how we can design the computer instructions. Now before starting the design, what do we mean by computer instruction? All of you know that a software program consists of a sequence of instructions. Now an instruction performs on stored data. That means a program is nothing but a sequence of operations to be performed on the data, and an instruction is one single operation on the data. So an instruction has two components. Normally we call the opcode field and the address field. Now opcode field defines the type of operation and it operates on the stored data. Address field contain one or more addresses of data on which the operation is to be performed, and data may be stored in a microprocessor register or in the main memory. So instruction has two fields, opcode field and the address field. So when we want to design a computer instruction or to represent a instruction, so actually we have to design the opcode field and the address field. That means which operation is to be performed and the operation to be performed on some data, where the data is stored, the address. So these two fields are actually to be designed. Now take one small example. Say I have one instructions, the move A0 to A1. I am considering or assuming A0 is the source and source address and A1 is the destination. That means I want the content of the address A0 is to be moved to the or as the content of the destination address A1. So my opcode field, that means which operation is to be performed, that is my move. So this is my opcode, and the source address and the destination address, that is the A0 and A1, these are my address fields. So the instruction moves the contents of the register A0 to A1. The number of instructions supported by a microprocessor depends on the size of opcode field. Now all of we know the computer can understand only a 0 or 1. So this opcode field, if this depends or the how many number of operations are allowed, that depend that what is the size of this opcode field. So the number of instructions or the number of operations to be performed or a number of operations allowed depends on the size of opcode. So this is very important when we will design the instruction set. So this is one of the things, important things to be considered, that what is the size of the opcode field. Say I have a 8-bit opcode, means one 8-bit number. So by 8-bit opcode we can specify 2 to the power 8, that means 256 unique instructions, as if every 8-bit represents one unique operations. What does it mean? Say I have a 3-bit opcode. So, I have a 3-bit opcode field. So, all possible 3 bits, say 000 to 111. So, these are my fields. Now, as if this 00 means one instruction, say I am telling add, say 001 means another, this is instruction 2, say instruction 2, so this is subtract, say 010 instruction 3, so this is some increment, 011 instruction 4, this is some decrement. So, like 100 represents something, 101, 110, 111. So, for by 3-bit opcode we can specify 8 different instructions or 8 different operations that are supported by this particular machine is a 3-bit opcode field. 8 different operations are supported. So, this is the meaning of that opcode field. Now, opcode encoding. So, a unique binary pattern, as already I mentioned that computer can understand only 0 or 1 and we use the binary systems. So, a unique binary pattern is assigned to each opcode by a process called opcode encoding. Just now I have given one example of a 3-bit opcode. So, one n-bit binary number can represent 2 to the power n unique opcodes. So, what now if I want to design this opcode part, so what is it necessary? I have some n-bit number and I want 2 to the power n unique opcodes. So, this is nothing but if I need a hardware, already we have seen that an n to 2 to the power n decoder is required for an n-bit opcode. Now, we take one example of a hypothetical instruction set. Say I have instructions move some clear register, reg means one register, add 2 registers, that means add the contents of 2 registers, register 1 and register 2 denoted as reg 1 and reg 2. Similarly, subtract the content of 2 registers and the content of 2 registers or the value of 2 registers, increment 1 registers, that means increment the value or the content of the registers by 1, and jump 1 address means this is an unconditional jump. Whatever be the condition irrespective of the condition, always this is a jump to this address. So, I have these 8 instructions. That means I consider one machine which allow these 8 primitive instructions. Now, move operations mean, say one content of register 1. So, when I give move operations, the content of register 1 is moves to content of register 2. So, this is denoted as reg 1 to reg 2. Now, clear register means it is a reset. So, this register or the content of this register becomes 0. Add reg 1, reg 2. Now, always this is conventional that after adding the content of 2 registers reg 1 and reg 2, the sum or the result of this addition goes to register 2. Similarly, subtract. So, the result of subtraction of the content of register 1 and register 2 move to the register 2. That means the content of register 2 now becomes the result of the subtraction. Similarly, AND OR, these are two operations, and this is the reg 1 and reg 2 and reg 1 or reg 2, and the result goes to reg 2. Increment reg. Normally, increment means the content of the register is incremented by 1. So, reg plus 1 means the content of register is incremented by 1, 1 is added with the content, and then the value is shifted to reg again. So, this is nothing but our add again. Only here, instead of one register, one fixed value 1 is always added. Now, jump address. So, this is PC means the program counter. This is the program counter. That means always the current, it contains the current addresses. So, address is goes to program counter. That means this is an unconditional jump to address. So, the address where I want to jump, now I give that value to the program counter, and we know that always the program counter contains the current address. So, it will be jump to that particular address. So, these are the meaning of these instructions. So, if we give these instructions, the what operations to be performed, that are being specified by this right hand side expressions. Now, if I want to design the instruction set, that means I need some binary value to be assigned for each instructions. So, means this binary value means this is the instructions. So, I have 8 instructions, say move, clear, add, sub, and or, increment and jump, and as there are 8, so as 2 to the power 3, 2 to the power 3 is 8, 2 to the power 3 is 8. So, I need a 3-bit binary numbers to represent 8 instructions. Now, this is the 3-bit opcode. This is the 3-bit opcode. Say I am telling these are my I0, I1 and I2. Say this is my I0, I0, I1, I2. Now, move means 0, 0, 0. That means when the opcode field contains a 0, 0, 0, that means the computer understands that this is a nothing but a move instruction. Similarly, if the opcode field contains a 0, 0, 1, then it is nothing but a clear, means reset to 0. The register value is reset to 0. Similarly, 0, 1, 0 is add, 0, 1, 1 is sub, 1, 0, 0 is AND, 1, 0, 1 is OR, 1, 1, 0 is increment, and 1, 1, 1 is jump. So, if more number of instructions are allowed by a processor, say here it is a only 8 instructions. So, we know that 2 to the power 3 is 8. So, log of 8 base 2, that many number of opcode fields are needed. So, if there are m number of instructions are allowed, m number of instructions or the operations to be performed. The operations are allowed or are supported by a processor. Then the opcode size should be ceiling of log 2 base n. So, this is the number of bits necessary for a opcode. So, these are the, in this way we can decide what will be the size of the opcode field of the instruction set. Now, we want to design this thing. So, that means we need a hardware for this opcode field. So, just the example we have shown, the hypothetical example, we have 8-bit instructions and we have seen we need 3-bit opcode for that. So, we have a 3 to 8 decoder is necessary, which has this 3-bit opcode, and there will be 8 lines for 8 instructions. So, these are my 0, 1, 2, 3, 4, 5, 6, 7, that 2 to the power 3 values, and 0, 0, 0 means this was a move, it was a move instructions. Then 0, 0, 1 means this is a clear, 0, 1, 0 means 2, that is a add, 3 is a subtract, 1, 0, 0 means 4, that was an AND, 1, 0, 1 is OR, this is a 6 means 1, 1, 0 is a increment, and this was a unconditional jump 1, 1, 1. So, this is my design of opcode field. The opcode field of instruction set. So, that we need only a n to 2 to the power n decoder for supporting 2 to the power n number of operations or a n bit opcode. So, opcode encoding, say I have a 16-bit instructions, and I have designed like that 5-bit, the 5-bit opcode field, and so 11-bit address field and 11-bit address field. So, as 5-bit opcode, So the operations supported are 2 to the power 5, means 32 operations are specified, and they operate on the data which are stored on this 11-bit address field. So by 11-bit addresses, I can specify 2 to the power 11 means 2048 memory locations. I can specify 2048 locations. So on these 2048 memory locations, data can be stored and the operations to be performed on these data. That means the operations that are specified by this 5-bit opcode, they access the data from these memory locations. Now, if opcode field is 4-bit, initially it was 5-bit, now it is reduced to 4-bit. So, my address field becomes 12-bit as the instruction set is a 16-bit. So, this is a 4 plus 12, 16-bit, because I have the instruction set has two parts, one is opcode, one is address. So, for 4-bit operations, 2 to the power 4 is 16 operations with access to 2 to the power 12. 2 to the power 12 means 4096 locations. That means the data stored on these 4096 locations are being operated by these 16 operations. Now, number of operations reduced to 50%. So, when it was 5-bit, there are 32 operations can be supported. Now, the opcode field is reduced to 4-bit. So, there are 16 operations. So, the number of operations reduced from 32 to 16 means 32 to 16 means 50% reduction. Now, number of memory locations, because as the opcode field decreases, obviously the address field increases. So, the number of memory locations increased to 100%, because earlier number of locations were only 2048 2 to the power 11, now it becomes 4096 means 2 to the power 12. So, it is now it is increased to 100%, double. Now, this concept is used in designing instructions with expanding opcode technique. This is called the expanding opcode technique. Now, we consider an instruction format with 8-bit instructions, 8-bit instruction length, and a 2-bit opcode field. So, address field is 6 bits, that means the full length is instruction set, the full length is 8-bit. This is opcode, this is address. So, this is the thing. So, opcode 2 bits can be 00, 01, 10, 11. Now, these 6 bits we are dividing into 2 address fields, 3 bits each. Say we are representing this thing by x0, x1, x2, y0, y1, y2. So, this is one address, address 1, y0, y1, y2, this is address 2. So, this is for 2 address instructions. We call this is a 4 2 address instructions. Now, how many different representations can be there with this 8-bit instruction length? Okay. So, this is, remember, this is one simple thing is a 4 2 address instructions. Now, what we do, that whether it can be represented by a 3 2 address instructions. So, instead of 4, so we are considering 3 addresses. Say I am taking 0 0, say the last one, as if the last one I am deleting. Say I have only these 3 2 address, this is a 3 2 address instructions, 3 2 address instructions. Now, say I am representing this thing in a different way, as if, say, these 2 opcode bits and the first 3 address bits, it is a 2 address. So, the first address we are taking, and as if this becomes a 5-bit opcode, this becomes a 5-bit opcode. Then only these 3 bits of address 2, that actually represents the address field of the instruction set. So, these 3 2 address instructions I have modified, that as if my opcode field extends its length up to the 3 bits of the address 1, and it becomes a 5-bit opcode. So, what it becomes now, that actually my instruction format is like that. My instruction format will be, say, 1 2 3 4 5, up to this 5, this is my opcode, and say these 3 fields, actually the address. So, this is actually the address 2 of the previous one. So, the address 2 of the previous one was the y0, y1, y2 fields. So, it has 0 0 0, 0 0 1, these are the 8 different values it can take, 8 different values, these are the 8 different values it can take. So, for these 8 different values, this 5 bit can be of this type. Say I am giving the first, that was the first 2 bit opcode, the first 2 bit, and these were the actually the address one. The next 3 bit, this becomes, see, as if this is always 1, one one, one one, and for this the next, that this 3 bit of address 1, they are changing. So, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. So, these are, now this becomes the, this becomes my, these 5 bits becomes my 5 bit opcode. These are my 5 bit opcode. These are my 3 bit address, 3 bit address, 5 bit opcode. So, this is one instruction format. So, 8 one address instructions, we can tell this is 8 one address instructions. Because there are 8 bit and this is only one address one, address 2 becomes only the one address. So, this is a 8 number of instructions and this is a one address instructions. So, earlier we have shown that this is a 3 2 address instructions, and here that can be modified or that can be represented as a different way, that 8 one address instructions. Now, we give the most important instruction set, or the microprocessor developed on this concept of the reduced instruction set, how they can be designed, or what is the concept of that RISC processor, we will discuss that thing. So, reduced instruction set computer. Now, RISC stands for reduced instruction set computer. This we can define as if this RISC is a generation of faster and inexpensive machine. So, the main concept is, or that is the basic principle for the evolution of RISC, is that RISC is for to cost less yet run faster. Now, at the cost of what? By using a small set of simple instructions for their operations. So, mainly we are discussing the design of the instruction set, and just now we have seen that mainly the opcode or the size of opcode that gives the number of operations or number of operations to be performed. So, by using a small set of simple instructions for their operations, that is the basic principle of RISC machine, which makes it faster as well as the less costly. Now, RISC allows a balance between hardware and software. We will see. So, mainly RISC is based on 6 principles. What are the principles? That reliance on optimizing compilers, few instructions and addressing modes. RISC, as its name implies, it is a few instructions, and we will see later that what do you mean by addressing modes. There are also very less. Fixed instruction format. It is not of a variable format like the complex or the old machines, complex instruction set machines or the old machines. It has a fixed instruction format. Now, instructions executed in one machine cycle. Only call or return instructions can access memory, and this is totally hardware control. As it is a hardware control, so this is the point that why it is faster, because as it is a hardware control, it becomes much faster. So, these are the 6 basic principles on which the RISC machine is developed. Now, before we go in details the RISC instruction sets, we define the MIPS and MFLOPS. MIPS is millions of instructions per second. As we are discussing the computer design of computer instruction sets, so how many instructions can be executed per second or per unit time, that is one very important thing, because mainly the speed of the processor, it depends on that. So, what we are telling that RISC machine is very is faster. So, it depends, this is some units, that how many instructions can be executed per second. So, easy to understand and to market, and the instruction set dependent, and this cannot be used across machines, and this is only the program dependent. Another important thing nowadays is the MFLOPS, means the how many floating point operations it can support, or it is possible to execute the number of floating point operations per second, that we are defining as MFLOPS. So, this is less compiler dependent than a MIPS, because it is a some only floating point operations unit. So, whenever floating point operations will be there, it will be executed by that particular unit, not the compiler. Not all floating point operations are implemented in hardware on all machines, but if it is implemented in hardware, then obviously that becomes or that makes the computer faster. Not all floating point operations have same latencies. Obviously, different operations have different complexities, so it will take different time. So, normalized MFLOPS uses an equivalence table to even out the various latencies of floating point operations. Now, always the trend was the complex instruction set computer. Now, because of their complexity, more hardware would have to be used for CISC, the complex instruction set computer. However, because of the more instructions, the more hardware logic is needed to implement and support them. it has more instructions. So, hardware will be more. Say for an example, and RISC machine, an add instruction takes the data from register only. As I mentioned that the data can be stored either in registers or the main memory. Now, register means it has some fixed, say, binary values. It is some binary numbers that is stored in a register. Now, the RISC machine can take only the data. Say I am using the addition. So, it has the two operands, op 1 and op 2, and this means two data, it is taking from the register only. Whereas, the CISC supports, because it is a complex instruction set, say the data can be in different form. So, when the data is accessed, first it has to be decided that in which form the data is. So, it has to take some decision, and some, if it is by hardware, then some complex hardware is needed just to decode the form of the data. So, complexity will increase, hardware will increase, the speed will less, because it is and it becomes expensive. So, that is the main difference from the complex instruction set computer, and why that reduced instructions in computers are evolved. Earlier, these are the some of the examples of the CISC machines, the VAX, Intel x86, and nowadays all the machines are of RISC. There are MIPS machine, DEC Alpha, the SunSpark, the IBM machines. These are all normally the all RISC machines that are nowadays the machines are available that are all RISC. Initially, they are only the power PCs or the desktop workstations are the RISC machines, but nowadays that all computers are that of RISC type. So, if we summarize the comparison between the CISC and RISC, so it has some the main differences lies the CISC has variable length instructions. It has a variable length instructions, whereas this is a fixed instructions. We call the single word instructions, or we can tell this is it has a fixed instruction format. Similarly, the variable format and fixed field decoding, the format is fixed. Now, the CISC is memory operands, means the operands, the data just now I told that is stored in the memory. So, the operations to be performed on the data are accessed from the memory, and this is a load store architecture. So, this is the main thing, or this is the RISC is a load store architecture. So, here all the data are stored on the register. So, the operations to be performed on the data are accessed from the register. It has some complex operations, and these are some simple operations. So, this is the main differences lies between the design of CISC and the RISC. Now, we consider the instruction set design, because we are mainly discussing on the instruction set. So, what are the design constraints? So, small and slow memories, compact programs and fast, and they are fast, because if it is a small memory, then the accessing will be the maximum access is restricted by the size of the memory. As it is a very small, so only less number of accesses are needed, so it will be fast. Small number of registers, because as already we mentioned the RISC operands, that is the one concept, the data are stored on the registers. Now, attempts to bridge the semantic gap the model high level language features in instructions. No need for portability, the same vendor application, OS and hardware, and the backward compatibility. Every new ISA, the instruction set architecture, must carry the good and bad of all past ones. So, powerful and complex instructions that are rarely used. IC technology and microprocessors in 1970s, they are of lower cost, low power consumption, higher clock rates, cheaper and larger memories. So, mainly to utilize this advancement of technologies, the RISCs are evolved. Now, another very important concept is there in the evolution of the RISC. So, one processor have a number of instructions or the operations allowed. Now, the research have been done that what are the frequencies of uses of different type of instructions. See, here one example is given. So, some instruction, these are the instructions. So, this is a load, and the average percent of the total execution, it has been computed that 22% of the total execution is a load instructions. Now, a conditional branch means if a condition is satisfied, it goes to some address. This type of instructions are executed 20% of the total execution. Similarly, a compare has 16% execution, store is 12%, add is 8%, and is 6%, a subtract is 5%. See, add is more, addition is more than subtraction. Move register to register, it is only 4%. A call routine is only 1% and return is also 1%. Total say 96%. There are many miscellaneous other instructions that are the rest 4% are of that type. Now, on these observations or this research, we will see that actually the load is 22%. That means the maximum execution or the maximum percentage of execution is of load instructions. See, store is of 12%, it is of actually. So, now people can make the all operations whether can be made or the design can be made of load store type. Using load store only, whether the instructions can be developed. All other instructions can be developed based on these two. So, this is a very important thing. This is a some top 10 86 instructions are observed, and the percentage of execution has been computed, and it has been seen that the load and store has more number, has greater percentages used. So, this is another important point, that why it is based on or why it is a load store architecture. So, if we summarize that instruction set design, so the very large scale integration, that means for the advancement of VLSI, that chip can be of small size, and then microstore occupies 70% of chip area. So, replace microstore with resistors, the low store. So, more resistors can be implemented. Increase difference between CPU and memory speed. Complex instructions were not used by new compilers, and software changes are reduced reliance on assembly programming. New instruction set architecture can be introduced. Standardized vendor independent operating system, and the academics and research, the need for portability. So, early RISC projects, the IBM 801, the Berkeley RISC 1 and RISC 2, and the Stanford MIPS, they are they developed, or some research is based on that preliminary machines based on the RISC instruction sets. Now, one we are taking one example, that is the MIPS machine. The MIPS instruction formats, or what we can do, that there is actually this, if we take one example of any one of these RISC machine, say that Stanford MIPS or our Berkeley RISC machine, will discuss that actually how the RISC machines are, or the designed, or how the instruction set of this RISC machine is designed, what is the formatting of the instruction set, etc. Now, we will see the quiz of this class. So, we have discussed mainly the instruction set and the instruction format, and the opcode encoding, particularly the expanding opcode technique. So, based on that, our quiz question is, so the instruction length and the size of an address fields are 9 bits and 3 bits respectively. Is it possible to have 6 2 address instructions, 15 1 address instructions, and 8 0 address instructions? So, one instruction length and the address bits are given, then whether we can construct the instructions such that it can specify this type of instruction sets. So, this is the quiz questions of lecture 33. This class will continue the discussion on the design of computer instruction set. So, so far we have seen the what is the format of a computer instruction, what are the two parts or two fields of a instruction, and how the opcode part, the instruction opcode is encoded. And then we introduce the reduced set instruction computer, and what are the different RISC machines so far developed. Now, already I mentioned that nowadays almost all the high performance computers are the RISC machines. So, just to see what are the basic architecture of RISC, some early machines developed based on RISC, we will see that thing. So, some early RISC projects are IBM machine and the Berkeley RISC-1 and RISC-2 machines and Stanford MIPS. So, this class we see as an example the MIPS architecture. So, the MIPS instruction formats, that all MIPS instructions are 32-bit long. So, this is the instructions are 32 bits. The three instruction formats are R type, I type and J type. So, it supports three different instruction formats, and the different fields are op means operation of the instructions, that means which operation are supported or which operations are currently being executed by the instruction. RS, RT, RD, the three source and destination register specifiers. Then shift amount, SHAMT, is a shift amount, that is a different field kept in MIPS. Another is funcT, it selects the variant of operation in the op field. Then address and immediate, that means address offset or immediate value, that means the data, or this is some kind of mode of operations, that whether it is the immediate value is being operated on, or the address is given or address offset, and from some addresses the data have to be accessed before it operates.